If we draw a graph with speed on the vertical axis and time on the horizontal axis, then we call this a speed-time graph. Let's add some scales to these axes and look at a speed-time graph for a runner during a race. So during the race, we have a speed-time graph that looks something like this. In the first section of the graph here, the runner's speed starts at 0 and then it goes up to 8 meters per second. If your speed is changing, we say there's an acceleration. So in this section, the runner accelerated from 0 meters per second to 8 meters per second. So in this part, they were accelerating. In the second section of the race, their speed didn't change. It remained at 8 meters per second. So we could say that in this part, they had a constant speed. A moment ago, we said that if there's a change in speed, then there's an acceleration. So if there's no change in speed, as in the speed is constant, there'll be no acceleration. So we could also say that in this section of the race, they were not accelerating. Then if we look at the final section of the race, this one here, their speed was at 8 meters per second and it came all the way down to 0. So in this section, they were decelerating. We're able to work out the numerical value of the acceleration at each stage in this race. We can do that because the acceleration is equal to the gradient of the speed-time graph. So if we want to work out the acceleration of any particular part, we just need to work out its gradient. Let's start with the first section of the race, between 0 and 5 seconds. Here we can work out the gradient by drawing a gradient triangle. The change in y is this part here, which goes from 0 to 8. So that's 8. And the change in x is from 0 to 5, so that's 5. We can then work out the gradient, which is the acceleration, by doing the change in y, which is 8, divided by the change in x, which is 5. And 8 divided by 5 is 1.6. So the acceleration in that first part of the race is 1.6. The unit we give to acceleration is meters per second squared. Now if we turn our attention to the second part of the race. Earlier we said that this part has a constant speed and no acceleration, in which case the numerical value for the acceleration must be 0. So we could say the acceleration is 0 meters per second squared. Now let's look at the final section of the race. Here we're going to draw a gradient triangle again. The change in y is this part here, which goes from 8 all the way down to 0, so that's a change of -8. And the change in x is this part here, which goes from 25 to 45, which is a change of 20. So the gradient of this line, which is equal to the acceleration, is the change in y, which is -8, over the change in x, which is 20. -8 over 20 is -0.4. And once again we use the units meters per second squared. The acceleration value here is negative because the runner was decelerating. A second thing that we can calculate from a diagram like this is the distance travelled. The distance travelled is equal to the area underneath the graph. So if we worked out this area here, we would know how long the race was. We can do this in two ways. Firstly, we could split this shape into some triangles and a rectangle like this. If we work out their areas, then add them together, we'll get the total distance travelled. But this shape is also just a trapezium, so we could use the area of a trapezium formula to work out the area. So for the formula for the area of a trapezium, I need to know the lengths of the parallel sides. The top and bottom of the parallel sides, so I'll do the top first, which goes from 5 all the way to 25, so that has a length of 20, and then on the bottom we go from 0 all the way to 45, so that's a length of 45. We also need the height of the trapezium, which goes from 0 to 8, so that's a height of 8. We can then just use the formula to work out the area of the trapezium, which is equal to the total distance travelled. So we could say the distance travelled is equal to, and then we do the area of the trapezium formula. So 1/2 multiplied by the sum of the parallel sides, so 20 plus 45, and then multiplied by the height, which is 8. To work this out, we do 20 plus 45 first, which is 65. Then we could do half of 65, which is 32.5, and then multiply this by 8, which is 260. We just need to add on the units for this, so since the speed was in meters per second and the time was in seconds, the distance travelled must be in meters. So the total distance of this race was 260 meters. It's worth mentioning at this point that sometimes an exam question may use the word velocity instead of speed, and call this a velocity time graph. For the purposes of the Gcse course, velocity and speed are essentially the same thing. But in most cases, exam questions do call it a speed time graph. Let's have a look at what an exam question could look like for this topic. So here we have a speed time graph, and we're going to do these questions. So part A says work out the acceleration of the car between 10 and 30 seconds. We know that the acceleration is equal to the gradient of the speed time graph. So we just need to find the gradient between 10 and 30 seconds. So at 10 seconds the graph is here, and 30 seconds the graph is here. So the gradient triangle would look something like this. The change in x goes from 10 to 30, so that's a change of 20, and the change in y goes from 25 to 30, so that's a change of 5. We then do the change in y divided by the change in x, so 5 divided by 20, which is the same as 0.25. So the answer to this one would be 0.25 meters per second squared. In part B of this question, we've been asked between what two times is the acceleration the greatest? Well, since we know the acceleration is the gradient of the speed time graph, the greatest acceleration will be the part that has the greatest gradient. Looking at the graph, I can see that this part here is the steepest line, so it must have the greatest gradient and therefore the greatest acceleration. This part is between 0 and 10 seconds, so the answer is between 0 and 10 seconds. In the final part of the question, we've been asked to work out the distance the car travels in the final 40 seconds. The distance travelled is equal to the area underneath the graph. So to work out the distance in the final 40 seconds, we want the area in the final 40 seconds that's underneath the graph. So that's this area here. This shape is also a trapezium, but you could think of it as being on its side. So if we work out the lengths of the parallel sides first, we have this one and this one. The first one goes from 0 to 30, so that's 30, and the second one goes from 0 to 10, so that's 10. The height of this trapezium will actually be this distance here. You could think of this trapezium just being on its side. So the height is from 40 to 80, which is 40. We then use the formula for the area of the trapezium, which is 1/2, multiplied by the sum of the parallel sides, so 30 plus 10, multiplied by the height, which is 40. And this gives you a total of 800, so the answer is 800 meters. Let's try a second example. So this time we have a different looking speed time graph and these questions. In part A, it says work out the acceleration of the cyclist between 50 and 70 seconds. Remember, the acceleration is equal to the gradient, so we just need the gradient between 50 and 70 seconds. So we've got this point here at 50 seconds and this one at 70, so a gradient triangle between those two. The change in x goes from 50 to 70, so that's a change of 20, and the change in y goes from 8 to 12, so that's a change of 4. The gradient is equal to the change in y, which is 4, divided by the change in x, which is 20. 4 divided by 20 is 0.2. So the answer to part A is 0.2 meters per second squared. In part B, it asks us to explain what's happening between 20 and 50 seconds. So what's happening at this section of the graph? Well, we can see here we have a horizontal line, which means the speed is constant at 8 meters per second, which means there's no acceleration. So we could simply say, the cyclist has a constant speed. Or you might also say, there's zero acceleration. In part C, we need to work out the total distance travelled by the cyclist in the 70-second ride. This time we want the total distance of the entire journey. So we want the total area underneath the entire graph. So we want this area here. To do this one, I'm going to split it into multiple sections. I'm going to draw some vertical lines here, and we now have a triangle, a rectangle, and a trapezium. So we're going to do each of those areas separately and add them together. So let's label each of these shapes, the triangle as A, the rectangle as B, and the trapezium as C. We'll begin by working out the area of triangle A. To do this, we'll need the base of the triangle, which goes from 0 to 20, so that's 20, and also its height, which goes from 0 to 8, so 8. We then do 1/2 multiplied by the base, which is 20, multiplied by its perpendicular height, which is 8, and this gives you a total of 80. Now if we move on to the rectangle, this is just the base, which goes from 20 to 50, so that's 30, and then the height from 0 to 8, which is 8, and we multiply those together, so 30 multiplied by 8, which is 240. Then if we move on to the trapezium, so here we need the sum of the parallel sides, so this one here goes from 0 to 8, so that's 8. This one goes from 0 all the way to 12, so that's 12. And the height once again goes horizontal because this trapezium's on its side, so that's from 50 to 70, which is 20. Then we use the area of a trapezium formula, 1/2, multiplied by the sum of the parallel sides, so 8 plus 12, multiplied by the height, which is 20. And this one will give you 200. So we can now work out the total area by adding all of these together. And if you add all of those together, you get 520. And remember, the total area is equal to the total distance travelled, so that's the answer to the question. Now we're going to take a look at a very different type of speed time graph, one that looks like this, and we've got these questions to answer. The first thing that you may notice from this is that rather than being straight lines, this line is a curve, and that's going to change our approach. So in the first part, part A, we need to find the acceleration when t is 20. You can see that when t is 20, the speed is 25 meters per second. It probably feels tempting to draw a straight line here and work out the gradient of that, especially based on what we've done up to this point. But that would be incorrect. We need to work out the acceleration at the instant when the time is 20. To do that, we need to draw a tangent to the curve at the time when t is 20. So a tangent to the curve at the time when t is 20 would look something like this. A line that just touches the curve at the point when t is 20. Then to find the acceleration, we find the gradient of this line instead. Now this can be a little bit tricky. What we're going to do is identify two nice points that are on this tangent. I'm going to take this point here because I can see its coordinates are 28 and 31, and this point here because I can see its coordinates are 4 and 14. It's advisable to pick nice points like this, but also make sure they're quite far away. In general, the bigger the triangle, the more accurate your answer is going to be. We then draw on a gradient triangle between these 2 points. So let's do the change in y first. This goes from 31 all the way down here to 14, so that's a change of 17. And the change in x goes from 4 all the way over here to 28, so that's a change of 24. We can now do the change in y divided by the change in x, so 17 divided by 24, which when rounded is 0.71 meters per second squared. You may have noticed that this question says we're finding an estimate for the acceleration. This is because we can't know the exact value now. It will depend somewhat on how you draw your tangent, and everyone's tangent might be slightly different. So in an exam question here, for instance, you may be looking for an answer that's somewhere between 0.6 and 0.8, assuming that my answer is very accurate. In the second part of the question, we're asked to work out the total distance travelled by the car. Now we know the total distance travelled is the area underneath the graph, so we need to work out this area here. Now once again, this is very complicated because the graph is a curve rather than straight lines, so we can't find this area accurately. Instead, the question says to use 4 strips of equal width. This is especially common if you do Excel. What this means is we're going to split the area under the graph into 4 equal width strips. You can see the time goes from 0 to 80 seconds, so if we split that into 4, that would be 20 seconds. So we draw vertical lines every 20 seconds like this to split that area into 4 equal strips. We then connect up the tops of each of these lines with more straight lines, and we end up with this purple shape here. Now the area of this purple shape is going to be close to the area underneath the red curve. So we're going to use this instead, which is why again the question says an estimate. So now we find the area of each of these 4 purple shapes. We've got shape A here, which is a triangle, and then shape B, C, and D, which are all trapeziums. So let's begin with shape A, which is the area of this triangle. The base here has a width of 20, and the perpendicular height is 25. So we do 1/2 times the base times the perpendicular height, which gives you an area of 250. Then if we move on to shape B, which is a trapezium, we need the 2 parallel sides. I've already labelled one of them at 25, the other one over here is 30, and the width here is 20. So we do 1/2 multiplied by the sum of the parallel sides, so 25 plus 30 multiplied by the height, which is 20. This will give you a total of 550. Then we move on to shape C, which is also a trapezium, and you'll notice that once again I've already got one of those parallel lines, and the other one is 26. The height is once again 20. So we do 1/2 multiplied by the sum of the parallel sides, so 30 plus 26, multiplied by the height, which is 20. And for shape C, that gives us 560. And onto the final trapezium, shape D. We've got the 26 for one of the parallel sides, and the other one is 15. And once again, the height is 20. So we do 1/2 multiplied by the sum of the parallel sides, 26 plus 15, multiplied by the height, which is 20. When you work this one out, you get 410. So to get the total distance travelled, we want the total area, so we add all 4 of these together. And the total for all 4 of those is 1,770 metres. Once you've worked out an area like this, it's quite common for an exam question to follow up with something like this. We might have part C, which says, is your answer to part B an overestimate or an underestimate? So the real area under the graph is this one here. But we didn't work that one out, we worked out this one instead. You can see there are some small pieces of area that we didn't consider, like this part, this part, this part, and even this part in here. So if we wanted to find the real area, we would need to work those out as well and add them on, in which case our answer is an underestimate because it's slightly lower than the actual answer. So we could say for part C, it is an underestimate. If it asks you to give a reason for your answer, you just explain that there are some extra bits of area that we didn't work out between the triangles, trapeziums, and the actual curve. It is possible in some questions that when you work out that distance travelled, it may be an overestimate. For example, if the curve looked like this. If we were asked to find the distance travelled for this one, we might split it into 4 equal strips like this, connect up the tops of those lines, and then work out this area here. Now if we worked out this area, we've actually done more area than we were supposed to, because we've worked out this part and this part as extra. In which case this one would be an overestimate for the true area. It just depends if the area that you work out contains more area than the real one or less. Now let's take a look at one final exam question. So in part A of this question, it says to work out the average acceleration for the first 20 seconds. Based on what we did previously, you might be expecting to draw a tangent to the curve at 20 seconds, something that looks like this. But that's not actually what we do. In this case, it said to work out the average acceleration. So we don't want to know the acceleration at t equals 20 seconds, but we want to know the average acceleration for the entire first 20 seconds of this journey. To do that, we do draw a straight line from wherever the curve is at 0 and wherever the curve is at 20, so something that looks like this. So the gradient of this line will represent the average acceleration for the first 20 seconds of the journey, as opposed to the instantaneous acceleration at the time when t equals 20. So to work out the gradient of this, we want a gradient triangle, and we can see the change in y here goes from 0 to 5, so that's 5, and the change in x goes here from 0 to 20, so that's 20. So the gradient will be the change in y, 5, over the change in x, 20, which is 0.25 meters per second squared. Let's try a second example of this. Work out the average acceleration for the first 30 seconds. So this time we connect up with a straight line, the point on the curve at 0 seconds to the point on the curve at 30 seconds. So it will look something like this. Once again, we need a gradient triangle. The change in y is here, that goes from 0 all the way to 12 this time, and the change in x goes from 0 all the way to 30. So we do the change in y 12 divided by the change in x 30, and this gives you 0.4. So 0.4 meters per second squared. I've put this question in just to highlight the difference between the instantaneous acceleration, which is at a particular point where we use a tangent, and the average acceleration, where we connect up 2 points with a straight line. In part C of this question, it asks us the times when the acceleration is equal to the answer from part B. In part B, we got the answer of 0.4 meters per second squared, which came from the gradient of this line here. So we've been asked to work out the times that have the same acceleration, so they must have the same gradient. So we want to find the points on this red curve where the gradient of the tangent is equal to the gradient of this purple line. So we could imagine moving this purple line so that we draw more parallel lines until it makes a tangent, like this. So one of the answers is at this time here, which is 27.5 seconds. There's also a second possible answer. If we move the purple line down like this, but once again keep it parallel so it has the same gradient, you can see it'll become tangent to the red curve at this point here, which has a time of 15.5 seconds. So we get two answers to this, 27.5 and 15.5. Both of these points would also have an acceleration of 0.4 meters per second squared because they have the same gradient.